Hello, this is Adam Sigler. I'm the Water Quality Specialist for MSU Extension, and I'm going to give you an introduction today on watersheds and water quality. And if we start off by thinking about this picture of a drop of water that I took while I was filtering a sample that I was about to send to a lab for analysis, and one of the things I was measuring was nitrate, for example. And I got back a result here that said non-detectable nitrate. But if I start to think about it, even with our most advanced analytical methods, with non-detectable nitrate in this drop of water, there could still be billions of molecules of nitrate in there. Because if we think about Avogadro's number, there are 10 to the 26 moles of substance in just a gram of water. Those are big numbers, and which leads me to think about the fact that a drop of water has a chemical memory embedded in it that we can understand with analysis and learn about the path that drop of water is taken to where it is. And if we look at this other drop of water, it's got color to it, so we might immediately surmise it's got bad water quality. But if we think about it a little bit more differently, this is a drop of coffee, actually, and right this minute I might be very interested in the concentration of caffeine in that water, leading me to prefer the quality of this water. This is all just to say that waters have very different qualities, which are important for different uses and also different natural water quality. So 70% of their surface is covered in salt water, which is great for marine life, but is not directly useful for us as humans for drinking, for example. And that's more than 97% of the water on the planet. Another 2% is tied up in ice, not directly useful for us. And less than 1% is what we have left. And if we think about how that water moves around the planet, when we're out doing our water monitoring, we're typically thinking about rivers and lakes, and these are small fractions, tiny fractions of a percent of the total water available on the planet, underlining the need for us to be good stewards of these limited water resources. And so if we're thinking about these rivers and lakes, then all of this water starts out as precipitation. And when that falls on the surface, a couple things can happen. It could either go back into the atmosphere as evaporation or transpiration, it could infiltrate and could influence groundwater quality, or it could run off over the surface. And when water runs off over the surface, it can carry things with it into our streams that can control our water quality. And so here we can see two streams mixing with visually very different water qualities here due to sediment. And to understand that stream water quality, we need to look at the natural characteristics and the land use within the watershed. So this concept of a watershed is critically important to understanding stream water quality, where these areas are delineated by a point on a stream, and then we look upstream from there to all of the land area that contributes water to that point on the stream. They're delineated by high points in the topography. And to look at an example, here is a watershed that's an 8-digit hydrologic unit code, is one way to talk about this. And it might be hard to recognize this unless we put over a map that has some roads on it in towns that we're more used to looking at. So this is the town of Bozeman, and this is the Gallatin watershed. And if we think about, I don't know who recognizes what watershed this is, but it's the Madison, the Upper Madison. And these two watersheds are adjacent to one another. And it's really important to understand the concept of watersheds, because this drop of water that might fall in the Gallatin versus the Madison is going to flow either way from the divide into these rivers, and these two rivers have very different water quality. The Madison River has arsenic at 10 times the drinking water standard, and that is all coming naturally out of Yellowstone National Park, out of the fire hole. So two raindrops falling out of the sky and landing on just either side of this divide are going to result in water flowing through these streams with very different quality that we have to understand based on the headwaters, the watershed area for these. The water quality in the Madison actually doesn't get down to below drinking water standards for arsenic until it's all the way up in the northern part of Montana and the Missouri from dilution. Montana is very much a headwaters state. Where I sit here in the Gallatin, I'm in the upper Missouri. When we send water out to the Gulf of Mexico, there is also the Columbia River Basin on the other side of the Continental Divide, draining the Clark Fork area around Missoula. And then we also have a little piece of the St. Mary's, which drains to the Hudson Bay. So we're very much a headwaters state, and this water that we send out of Montana is used by many people multiple times downstream, which means we have a lot of responsibility to those downstream water users to send them high quality water. Thinking about water in the landscape, if we look out across our watersheds, the vast majority of areas are upland, and it's a pretty limited amount of water of our landscape that's wetland or riparian. But these wet areas of our landscape are disproportionately important. Wetlands, for instance, are very important both for acting as filtration systems to remove pollutants. They also are very important for groundwater recharge, where water is retained on the landscape in those wetlands and can recharge groundwater, something that's growingly important in areas where we have impervious surfaces in developed areas with roofs and pavement, concrete, and we're not recharging as much water to groundwater. So wetlands are very important for that, in addition to being very important for wildlife. Riparian areas we often think of as these threads of really green area down along streams. And these are transitional areas between the upland and aquatic ecosystems. And these are very important for a number of reasons, which we'll walk through here. One is that riparian vegetation is a natural filter system. This was a project I worked on some years back where a producer had livestock that were watering directly in the stream, and he was interested in putting in off-stream water, so he built this fence back here and fenced the livestock out of the stream, and riparian vegetation came in and thick and created a filter system where prior to the project, with a rain event, we would get increases in nutrients moving into the stream. But after the project, very soon after, with this vegetation establishment, similar rain event, no reaction in the stream with nutrients. So riparian vegetation acting as an effective natural filter. And riparian vegetation is also important for stabilization. We can see destabilized banks here because the vegetation had been altered in this case. And what that vegetation is on the banks really matters. If you think about sod that you roll out on your yard, how deep is that? It's only got about an inch of soil, and the vast majority of those grass roots are in that inch. So we need things that are more like sedges, rushes, or woody vegetation that have a lot more depth to their roots below the surface. And this is really important for some of those habitat characteristics we think about, like an undercut bank here, where the vegetation is holding the soils in place, and so the river can undercut the bank, and those habitat areas are critically important for those big fish that many of us like to catch. Riparian areas are also these river process zones. Rivers are very dynamic, or fluvial processes. So we think about this graphic here, the curviness of the stream over a given length of valley is the sinuosity of that stream. And we can see this here in this aerial image in the Gallatin Valley, where the stream is very sinuous. And this process of the stream moving back and forth creates these eroding banks on the outside of the curves. But then if we look at the other side, we get these point bars, and often we get this new vegetation forming there, creating this dynamic equilibrium where we have destruction of banks on the outside, creation of new land on the inside. And the result is this mosaic of vegetation of different ages in riparian areas, which is really important for ecology. And that's a natural process that we have to give rivers the room to do. We also need to give them room because flooding is a natural part of river processes. And you can see in this picture in the Gallatin Valley of the river at high flow spreading out in some of its former channels. This is dissipating the flood energy, is also recharging groundwater. Some really important characteristics. We want to back off from the riparian corridor and give the river room for these processes. Anybody that's spent time in riparian areas knows that they are rich areas for wildlife. Some, obviously fish, must live right in the water. Amphibians are obligate to be near the water as well. Many birds and a lot of critters just like to spend their time in the water and in and near the water. So a lot of the water quality management that we think about today is the result is framed around the Clean Water Act, which came around in the 1970s, largely because of things like this. The Cuyahoga River, made famous by the Time magazine article in 1969 as a river that oozes rather than flows, where this river was started on fire multiple times and they couldn't put it out because of all the oil and mill and paper mill waste floating on the surface of the water. And so in 1972, the Clean Water Act passed, and it addressed right off the bat point sources, which are these classic examples of a wastewater treatment plant that dumps water into a stream through a pipe. And so industrial sources, things that you can look at the pipe, you can sample the water quality there, and then go back upstream, find where it came from, and require those entities to have a permit. We're now to a point where more than 90% of our water quality issues come from non-point source pollution. These are things spread out across the landscape, which all of us are contributors to. And there is a really important distinction here that point sources, we've made dramatic improvements in those, and now we need to deal with our non-point source issues, which we all contribute to. And there's an important distinction with regulatory, where point sources are permitted, non-point sources are all dealt with under a voluntary framework. So we have to get people interested in addressing these issues if we're going to make headway on them. And so there are a lot of reasons for volunteer monitoring or citizen science to take place. And one of those is for fostering stewardship in the watershed, where we get people out to understand that there are streams running through our communities and making observations to realize that some of these streams have water quality issues in them, and that there are things that we as individuals can do to address those issues. And this is critical because there's no SWAT team coming in to address these issues. This is all voluntary, and we need to educate ourselves about what we can do and what others can do to address these issues. So thinking about what kinds of issues we have here in Montana, the Montana Department of Environmental Quality breaks the state up into over 1,000 assessment units. And we have 60,000 miles of perennial streams in Montana, a rich set of water resources. And approximately half of those are impaired with sediment. We also have some nutrient issues, nitrogen and phosphorus, and we also have a number of metals, a nod to Montana's mining legacy in many parts of the state. So there are all kinds of things that we can monitor in our water and all kinds of different issues that are unique to different watersheds, but I like to break them up into physical, chemical, and biological. And so physical water quality parameters are, we can think about things like the sinuosity of the stream and the size of the substrate that's there, whether the streams are connected to their floodplains and how much sediment they're moving down. Chemical could be anything on the periodic table, or and nutrients in that way, or emerging parameters of concern like pharmaceuticals, herbicides, or other products like that. Biology, we can think of both good and bad aspects of biology, where bugs like stoneflies and mayflies are a critical part of our ecosystem, and so we can look at how many of those are present and what their characteristics are as an indication of water quality. Bad bugs, I'm talking about things like waterborne pathogens like Giardia, where we have things that are from the feces of warm-blooded animals that can cause waterborne disease. And so we can monitor for those kinds of things as well. So I'll highlight just a few of the things that are commonly measured by volunteer monitoring groups, starting with sediment. So we're interested in sediment in streams because it relates to the habitat of the critters that live in the stream that we want to protect in those aquatic ecosystems. And so a classic way to think about measuring the amount of sediment a stream transfers is by taking a grab sample and then measuring how much particulate is in there. We can also take, in this case, this polarized lens to look at the bottom of that stream and see that there's fine textured sediment deposited there. That's kind of what we're doing when we take measurements like pebble counts in riffles or use a gravelometer, which is a way to do a pebble count. We can also think about doing things like pool tail fines, where we look at the amount of sediment that's on the bottom of the stream that those different forms of life, macroinvertebrates or fish, are experiencing as they're trying to live out their life cycles. We also commonly measure field parameters with a multimeter that might look something like this. Field parameters include temperature, pH, specific conductivity, and dissolved oxygen. These are things that we have to measure in the field because if we take a sample, these things can change. And so temperature, just a pattern we expect to see commonly in Montana is much cooler temperatures in the winter and much warmer temperatures in the summer, which might influence when we want to go swimming. It also influences the health of our aquatic ecosystems. And we also, we have these patterns on a seasonal basis for temperature. We also, in many cases, can expect to see these diel or daily swings in temperature. So it's really important to measure temperature when we collect water samples for interpreting those samples, but we have to be aware that temperature is swinging up and down on a daily basis. So if we really want to understand what's happening in a stream, we probably are going to need to measure it with a probe that measures daily, hourly data. Dissolved oxygen is what those fish and macroinvertebrates are breathing. It's the water the oxygen that's dissolved in the water. I've got this picture of bubbles here because it's kind of might make us think of dissolved oxygen or oxygen bubbles, but gas or oxygen that's actually in the form of a bubble is not actually dissolved. An interesting nuance there. Dissolved gas we can't actually see it, but it's critically important that for these ecosystems to be able to breathe. pH, or a measure of the concentration of hydrogen ions or the acidity. In most of our Montana streams, we're somewhere between 7 and 9. And that does a pretty good job we've got pretty well buffered water in Montana in general. So we tend to have reasonably conducive pH for our aquatic systems, but a bit of trivia, it is actually possible to have negative pH values, which often occur in extreme acid mine drainage situations. And the story that I heard about this picture of this shovel, which is dissolved right at the water line, is that it was left in the water overnight in this hyper acid system in California, and it dissolved that shovel at the water line. So specific conductance, how much electricity does a water sample conduct? And so to think about this, I've got this hot tub here that perhaps we're going to climb in and have a good time. We're really excited because we got our brand new boombox. And if I'm in this scenario, do you think that I would want to have this hot tub full of DI water, deionized water, or seawater? The answer is that I would want to be in deionized water because it is actually, pure water does not conduct electricity. And so if that radio fell in and I was in DI water, then it would be less likely that I would be electrocuted than if it was seawater, which would readily conduct the electricity. I probably don't want to do either one of those, but it's just a silly way to try and remind us that we've got this nice correlation between the specific conductivity of water and the total dissolved solids, or the total amount of salt in there. And so specific conductance, one of our field parameters, is a way to estimate the total amount of salt in the water, a general water quality characteristic. Discharge is another thing that we often measure, which is the amount of flow going by a point at a given time. And so USGS is a great resource for this, and we can think about our hydrographs over time, or the amount of flow going past a point for a given amount of time. And so we can visualize this as a cubic foot. A cube with 1 foot on each side is a common measure, and it's a CFS, or a cubic foot per second, number of cubic feet moving past a point in a second. So we can think about measuring this by measuring the width and the depth of a stream, and then measuring the velocity, which we can do with measuring how fast something like an orange moves through a reach, or with an electromagnetic meter that is using an electromagnetic field to measure how quickly the water is moving past a point. Discharge can control water quality in a lot of ways, and we can expect very different qualities of water at different discharges, but it's also really important in watershed management because if we think about this scenario where I tell you that there's 1,000 milligrams per liter of sediment in one stream and 10 milligrams per liter in another stream, and I want to know which one I should focus on to improve the sediment issue downstream, which one do you go to? Well, the answer is that we can't know. We don't have enough information unless we know the amount of flow. If this stream is only flowing 1 cubic foot per second and this one 1,000, then there's an order of magnitude more sediment moving down the stream. And even if we move that one to 0, it's not going to affect the overall amount of sediment moving downstream. So this is a calculation of the load. The concentration times the flow is necessary for us to calculate a contaminant load, which is how we want to think about pollution management in a watershed context. And so we started to talk about the fact that water has a memory, and there are so many interesting patterns in nature that we can explore by looking at water and thinking about the memory that it carries about where it's been. And another interesting pattern, so a general interesting pattern to think about is, in this case, flow. In Montana, we have commonly these spring snowmelt hydrographs where we have peak discharge in the spring associated with snowmelt. If we think about the amount of sediment, the concentration of sediment in that stream, when is it the highest? Many of you probably knew that sediment is highest when flow is highest. It's actually, the highest sediment concentrations can occur just before peak flow because of a rinsing of the landscape where we tend to rinse off all of the accumulated sediment, and that peak might occur just before peak flow. And then here on the falling limb of the hydrograph, we might have already cleaned out a bunch of the sediment and the concentration might be a little lower. A concept called hysteresis, if you're curious. What about total dissolved solids, or the amount of salt? When do you think that the lowest concentrations of dissolved solids occur? They occur in the spring at the same time near the highest concentration of suspended solids or sediment in the stream. And why do you think this would be? Well, it's because of dilution. If you think about the nearest thing that we have to deionized water in nature, or water with no salt in it, it's precipitation, either in the form of rain or snow. And in the spring, during snowmelt, all of this flow is coming from snowmelt, and so it's deionized water pulsing into the stream and diluting it. But what is it diluting? Well, out here at base flow, when the snow is melted, there's no more runoff coming out of the mountains from snow, all of that water in the stream is coming from groundwater. Groundwater tends to move more slowly, and it is in contact with minerals and can dissolve salts. So we tend to have higher concentrations of salt in groundwater, and in the fall, that's where almost all of the stream flow is coming from in many of our systems. So this is a very simplified version of these patterns, which are really interesting, I think, to think about. And so with that, I'd like to thank you for volunteering as a stream team member. It's really critical that we understand our water quality issues and get out in these water bodies and experience them, and then learn about what we can do to help protect them. So thank you for all that you're doing.